Happy Wednesday evening, Bearcats. All right, we're starting 1.6. This is about a library of functions. Much of what is in this section of the chapter is review, except with a little twist in terms of notation. So most of it's not real new. We do have a couple of types of functions you did not spend much time with last year that we will spend more time with this year. But a lot of it is just applying your past knowledge and using some different notation. All right, that's really true in our first example here. We're asked to write a linear function. In the past, you said write an equation of a line. Same thing, except we know it's a function, so we're calling it a function. And the way it's given to us is a little different. I want us to notice in this particular set, and you'll have examples in your classwork tomorrow as well as on the test, we're writing a linear function for f, where f of 1 is equal to 3. Well, we know f of what? What is f of 1? F of, this is your x value. When you plug an x value in, you get an answer, and that answer would be what this function is equal to, which would be your y value. So really what we have here is an ordered pair. We have the ordered pair 1, 3, and we have the other ordered pair 4, 0. And after this, it's basically writing an equation of a line. So you're going to get to practice a little bit of what you did in the last test. And some of you did really well in that, and some of you had trouble. So it's your turn to catch up and make sure you are 100% clear on writing equations of lines. All right, so the two things we have to have to write an equation of a line is a slope and a point. And remember, whenever we have two ordered pairs, we're going to label them now x sub 1, y sub 1, x sub 2, y sub 2. And we're going to be talking about slope. So our slope formula that you need to make sure that you know is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And that is the slope. All right, so we need a point and a slope. We're going to use the first point. So our point and slope, I'm going to put a box around the information we have to write the equation along. Our point we're going to use is 1, 3. And that point is our x sub 1, y sub 1. And now we need a slope. So we're going to have to use the 2 points that are given to us to find the slope. So we're going to plug into this equation and find our slope. So I'm going to go over here to the side and do that. So y sub 2 would be 0. Y sub 1 would be 3. And then we would have 4 minus 1 at the bottom, or x sub 2 minus x sub 1. And that would give us a negative 3 over a positive 3, which is really a negative 1 over 1. That's our slope. So we're going to go over here, and the slope is negative 1 over 1. All right, we now have our point. We now have our slope. We are now able to write the equation of the line. As I mentioned in the first unit, I really think using this slope formula in this form is best when you're talking about higher level math. You do not have a calculator. You do not want to have to worry about fractions. So I'm going to use this form one more time. And now I only have my y1, my x1, and my slope. And I'm going to substitute that in. So I'm going to go y sub 2, which I don't have, minus 3, because that's my y sub 1, over x sub 2, which I don't have, but minus 1, because that is my x sub 1. And now I know it equals a slope of negative 1 over 1. And now you'll simply cross multiply to solve. We'll go ahead and finish this up. So 1 times y would be y, 1 times negative 3 is negative 3. Equals, go the other way, negative 1 times x is negative x, and negative 1 times negative 1 would be a positive 1. To finish solving for slope-intercept form, you would add the 3 to both sides. The 3's cancel on this side, and your final equation is y equals negative x plus 4. Now, if you want to put it in function notation, you come over here and we could write it as a function, and instead of y, we could write f of x equals negative x plus 4. So there it goes. All right, we're going to go on to the next concept for the evening. All right, the next thing we do is a little bit new for you. Most of you, if you were in a pre-AP Algebra 2 class, you might have been exposed to this. Most of you, if you came from regulars, Algebra 2, all the way up here to this pre-cal college class, and you're becoming so smart already. I'm watching that happen more and more every day. We are going to deal with piecewise functions. We've talked about it a little bit this year. We've seen some graphs of piecewise functions. Piecewise functions, you'll notice up here it says, are functions whose graph resembles a set of stair steps known as step functions. And that's a particular kind of piecewise function. A piecewise function is a graph where there are several parts on the graph. The most famous step function is the greatest integer function. We're going to use this one a lot. Greatest integer function, which is denoted by the double bracket and the x in the middle. And it says f of x or y equals double bracket x. And it's the greatest integer. This is really important. You have this written in your notes. F of x equals double bracket x. And it means the greatest integer less than or equal to x. Less than or equal to x. That's really, really important. I will always tell you to think left. In other words, if you can imagine where you are on a number line and think to the left, the nearest integer to the left. Integers are counting numbers, 1, 2, 3, 4, whole numbers. The greatest integer to the left, or positive and negatives, the largest one, or the next one to the left. Just think left. So, for an example, we have a couple examples here. If I have the greatest integer of -1, that would be everything that is less than or equal to -1. Well, less than or equal to -1 would be -1. That is an integer. Here's where it starts to get interesting. If I have the greatest integer of -1/2, I'm going to imagine my number line, and I'm going to imagine -1/2. The greatest integer, you think to the left, would be at -1. -1 would be my answer. Think about that for a minute before we go to the next example. I'm going to erase. Oops. I'm trying to erase. My eraser. Let's think about the next one. This says 1/10. So imagine on the number line you're at 1/10. Think to the left. The next integer to the left would be +1, and 1 would be my, what am I saying? Would be 0. 0 would be my answer. And then finally, this last example. Is at 1.5. So again, I'm on a number line and I'm at 1.5. If I think left, 1 would be my integer less than that. So if it's a whole number or an integer already, then that would be your answer. But if it's a fractional part of anything, you've got to go to the left, to the next closest integer to the left. All right, let's go ahead and do these two examples. This should set you pretty straight for tomorrow's classwork on this section. So, on this one, we have 1/2 x plus 6. You do everything in the double braces and then go to the left to get your answer. So here we go. So for part A, I have k of 5. That means I have my little double bracket, and I have 1/2, and now I have 5 in for the x plus 6. 1/2 of 5 would be 2.5, so I have 2.5 plus 6. So I really have the greatest integer of 8.5. And to get my final answer, I think on a number line to the left, and the greatest integer to the left, the closest integer to the left of that would be at 8, and 8 would be my answer. Let's look at part B. For B, I'm plugging in -6.1. So again, I'm going to have my greatest integer, and I have 1/2 times 6.1, and that's on my -6.1. And then plus 6. When I go through and I figure out what 1/2 of -6.1 is, and I add 6 to it, I'm going to end up with the greatest integer of 2.95. So if you can imagine you're at 2.95 on a number line, that means you're close to 3, but you're not at 3. But you have to think to the left of that. If you're on that number line and you move to the integer left of that, that would be at 2. Alright, part C. And now we have, again, 1/2, but we're going to multiply times 0.1. And then we're still adding 6. So again, if I calculate 1/2 times 0.1 and I add 6 to it, I'm going to get 6.05. So the greatest integer of 6.05. Really careful here. Imagine you're on a number line at 6.05, 6 and a little bit. You need to go to the left. You need to go left. Think about left. If you go left, you'd be at 6. 6 would be your answer. And finally, part D. You have 1/2 of 15 plus 6. And now you have the greatest integer of 13.5. And again, if you think to the left, you would be at 13. All right, I would pause for a minute and I would make sure you understand that. And basically you're calculating everything inside the greatest integer function and then looking to the left on a number line. That's what you're going to think. It's the number less than. So you're going to the left. So you can pause. I'll be right here waiting for you when you get back. Okay. Hopefully you're kind of getting the hang of it. We're going to do another one. And I picked 2 of the more difficult examples. So many of the ones that you'll do tomorrow in class are actually a little bit less complex than this. So let's take a look at where we are now. All right, so now we have, for A, we have G of 1/8. Now, we're going to plug that in for X. And we have -7 on the outside of our greatest integer function. We're going to have 1/8 plus 4 inside, and then plus 6. I'm going to take a little extra time, and then we'll go a little quicker on the other one so you understand. You do everything in here first and figure out what that value is before you multiply or add the 6 to it. So I still have -7, and I have 4 to 8. The greatest integer of 4 to 8. Let me go and mark that off. Plus 6. All right. So the greatest integer of 4 to 8. To take care of this, go to the left, would be 4. That value would be 4. So then I would have -7 times 4, which would be -28, and then plus 6, which would end up giving me -22. -22. Think about that, but you went ahead and calculated everything inside, then you took care of what was on the outside. All right, B. B, we have G of 9 equals -7, and we would have the greatest integer of 9 plus 4, and then plus 6. So 9 plus 4 is 13. The greatest integer of 13 would be 13. So now you have 13 times -7. 13 times -7, I believe, would be -91 plus 6, and that would be -85. You may need to pause and think about those steps. All right, C. C is G of -4. I like all these whole numbers. It makes it easy. So now you're going to go, our integers, you're going to have -7, and you're going to have, instead of x, you will have -4, plus 4, and then plus 6. -4 plus 4 is 0. All right, so the greatest integer of 0 is 0. 0 times -7 is 0. So now you simply are just left with 6. And finally, D. Again, we have G of 1/2. -7, greatest integer, 1/2 plus 4 plus 6. So 4.5. Well, if you're at 4.5 on a number line and you think to the left, you'd be at just 4. So 4 times -7 is I'm sorry. Oh, that's 3/2, not 1/2, sorry. 3/2. So 3/2 would be 5.5. Would be 5.5. And 5.5, if you go to the left, would be at 5. So 5 times -7 is -35. And if you have -35 and a +6, you have -20. Think about that. That's the greatest integer function. All right, the last thing we're going to talk about is piecewise functions. And you, like I said, you saw a few of these before in graphs. We had one on our first test, but we really haven't had to graph them ourselves. We've just been given the information. So I want to talk about sketching the graph. And yes, I know it's over there, but I'm going to talk about how you find that graph. Piecewise functions are parts of graphs. So they're basically a graph, and then you've cut off part of it, or you've restricted the graph to just certain x values. So these right here are called our restrictions. Okay, and those are the only values that you can have. Those are our restrictions. So here we go. I can't figure out how to put a grid on here yet, but as soon as I do, I will. So right now, you're going to have to just do with me sketching. So the first equation I'm going to use is a linear equation, and you always want to identify what kind of equation so you kind of know what the shape of the graph should be. So 2x plus 3, and I want it for all values of x that are less than or equal to 1. So I'm going to actually just create some ordered pairs here. I'm going to erase this right here so we have a little bit of room. I'm going to create some ordered pairs for this one. So I'm going to always plug in the restriction. No matter if it's equal or not, I'm going to plug in the restriction. If it's equal, the dot on the graph will be filled in. If it's not equal, the dot on the graph will be open. So I'm going to put a 1 in. If I plug 1 in for x, 2 times 1 is 2, plus 3 would give me 5. So that would be the first ordered pair I would graph. So I would go to 1, and I would go up to 5. Which is compass of 1, 2, 3, 4. So 1, 5. And it's filled in because it was equal. I'm going to pick one more point. Since it's a line, I only really need 2 points. So I'm going to pick a value of x that is less than 1. This is going to be less than 1. It could be anything. Let's pick less than 1. Let's pick 0 would be an easy one. Let's just do that. So 0. It could be negative numbers as well. So 0 times 2 is 0 plus 3 would be 3. So at 0 we get 1, 2, 3. And like I said, it's a line, so all you really need is 2 points. So you start always at the restriction point, and you move toward the next point. So we would be moving this way. Let's see, I know. Should go to those points. All right, so that would be my first one, and this should be a nice, pretty straight line. That's pretty nice. All right, next is the second part of our function, which is still all one function, just a different piece. Hence the word piecewise. So now we're going to do the same thing, and we're going to start with 1 again. But this time when we graph it, we'll graph it with an open circle because it's not equal. So we're going to plug 1 into the second equation. So 1 with a negative part makes it negative 1 plus 4, which would be 3. So we're going to go to 1, and we're going to be at 3. 1, 2, 3. And we're going to open circle. And now we're going to pick a value of 1 greater than 1. So interesting might be a 4. If I put a 4 in there and put a negative, I have negative 4 plus 4, that would put me at 0. So at 4, there's 1, 2, 3, 4. At 4, I would be 0. And I would draw a line through those points. And that would be the second part of my function. And as you can see, it looks something like this graph. And that's how we would graph it. We always start with the restrictions. All right, the last page is really just a picture of all the different types of, not all, but many of the basic types of functions that you should be familiar with. So I'm going to take a look at that. Really, I think you should sketch these and have these written in your notes so that you can refer back to them. They don't need to be, exact sketches. They can be actually sketched. They don't have to be graphed on graph paper. But I just want you to be able to be familiar with all the different types of functions and what they look like in general. So we have a constant function, which is basically a straight, flat, horizontal line. Identity function, which we've referred to in the past as a linear function. The absolute value function, that V for value, that V for victory shape. The square root function. Sometimes I call that the teapot graph, and there's just one little arm. The quadratic function, which you're very familiar with. Cubic functions. You have not been that familiar with cubic functions. Cubic functions are kind of curvy. Reciprocal functions, we often called them last year, they were rational expressions. Rational expressions, and they were similar with this. You did a little bit of this last year. And then just what we talked about now, the greatest integer function. I'd make sure to have those in my notes and make sure that you're really clear about what each of those look like when you see a function, that you would kind of know what the picture of that graph looks like. All right, that's it for tonight. We will do this as an application tomorrow in class, and then we kind of have a little bit more intensive lesson for tomorrow night, so make sure you're taking notes. Take good notes, and you're going to be great. All right, have a great Wednesday evening. See you later, cats.